Okay, everybody. I would like to welcome you on behalf of the company Netz to today's webinar. And we're thankful that you could attend today and hopefully get some good information in the area of DSC of polymers. Today's webinar is going to feature the basic DSC analysis of polymers. We're going to look at things like operating principles of the DSC, the method itself, go into a bit of the theory and the mechanics of the method, and then we'll follow that up with applications for quality control and also failure analysis, and then we'll summarize and talk about some other things that are available for educational purposes from the company. So thanks again for being here, and it's really exciting and a great day to have you for the webinar. I'm your speaker for today. My name is Bob Fidler, and I'm with the organization called Netz Instruments North America. Our headquarters for Netz Instruments North America is in Burlington, Massachusetts, and my job for the company is technical sales and marketing. The headquarters for Netz worldwide, some of you may know, is based in Selb, Germany, and we are a subsidiary company of the parent, based in Germany, and our subsidiary is responsible for North America, again based in Burlington, Massachusetts. Myself, I've been with Netz now for quite some time. I started in 1997, so it's right about 19 years. So it's exciting, and it's been a great place to work. And I think what you'll find often with folks from Netz is that being here for such a long period of time is quite the norm. So it's just been a very wonderful place to work and learn about thermal analysis and to work with our customers. From an educational standpoint, I'm originally from Pittsburgh, Pennsylvania. So I went to the University of Pittsburgh and studied chemistry, finished there in 1985, and then got a master's in business from the University of North Carolina at Charlotte in 1994. Fundamentally then, I've got over 30 years experience with marketing and technical sales of analytical instruments, but more specifically now, about 24 years experience with thermal analysis instrumentation. Just to give you an overview of the company Netz and who we are, I think that's kind of important to see where we fit into the big picture for thermal analysis. Netz itself is a family-owned company for, gosh, over 140 years now. It's been held by the Netz family in Selb, Germany, and we're comprised of three different divisions. The division that I'm part of is called Analyzing and Testing. And in Analyzing and Testing, we've got a product range that's comprised of instruments for thermal analysis and then also for thermal physical properties measurement. And we're going to focus today on thermal analysis. There's other webinar series on thermophysical and thermal properties measurements. The two sister divisions of the company are grinding and dispersing, and then also pumps and systems that you'll see here. I won't go into too much detail on that, but suffice to say, the company got its start back in the 1800s in this area of Bavaria in Germany that's quite famous for high-quality porcelain production. And so that got us involved in the area of thermal analysis, starting all the way back in the 1950s. We started to develop some of the very first thermal analysis equipment to characterize this ceramics and porcelain materials. And we've, as the years have gone by, greatly expanded the line to get into areas, for example, the focus today on polymers. Just to give you a frame of reference, the company now is approximately about $550 million worldwide. Staff is about a little over 3,000 people now worldwide. And I think what's important to note is that probably close to 2,000 of which are based outside of Germany throughout the world. So Netz is a very globally acting, world-oriented company. So I think that's important, especially for all of us that are spread throughout the world, to know that Netz has a great support system throughout the world. The business unit that I'm again involved in is analysis and testing. We've got a product range that covers from as low as liquid helium temperatures, minus 260 C, up to extremely high temperatures, 2,800 degrees, for some of our equipment for thermal properties measurement. So in the area of thermal analysis, where we're going to focus today, we're looking at things like changes in dimension, mass, energetics or phase transitions, enthalpy behaviors, all as a function of temperature. In the area of thermophysics, we look at things like thermal conductivity, specific heat, and thermal expansion coefficient. We're also involved in calorimetry, so things like thermal safety, thermal hazard studies, looking at degradation reactions, temperature reactions for runaways, heat dissipation, and also pressure generated. And then finally, a fourth leg of the organization is involved in contract testing. Some of you may have been experienced with us in the area of fee-based or contract measurements. Our headquarters, again, in Burlington, Mass., has a tremendous contract testing laboratory where some people get introduced to us there. We also hold seminars throughout North America. We also, at our facility here in Massachusetts, are involved in training, but we also do on-site training, meetings, and then also consulting. So what we'll focus on today, after that brief introduction, is applications of thermal analysis, the DSC method, particularly in the polymers industry. It's probably the largest single market segment for this type of work. And we'll really dig into it and try to give you a better feel for how to use DSC in your daily work, areas where it can be useful, helpful, and then try to maybe give you some good background information as to how the instrument functions. And that might give you some ideas how to better apply it then in your daily work. The first thing we'll look at is in the context of thermal analysis for polymers is just kind of a general workflow in the polymer industry. What we're looking at is a kind of a characteristic overview of an injection molder. And I think what's really neat here is that you can see that there are lots of opportunities for DSC to play a part in every stage of the process, from delivery of the pelletized resin to the molder, all the way to storage, and then finally next drying and feeding. And then we get into processing and forming, and then the final product. And you can see the DSC is very important in the area of quality control. We can look at things like identify things like the type of polymer. We can combine that with other techniques like TGA to look at composition analysis. TGA is to look at mass change. DMA looks at mechanical properties. I think it's important to note here, everything you see in bold is an area of instrumentation that Netz is able to supply. So as we get a little bit further down this chain of work into the storage conditions, then we look at things like the effective humidity, for example. And we can do that with the TGA method, thermogravimetric analysis, to look at evolution, for example, of moisture. And then we go into to look at the properties of the material in the processing and forming stage, and then also in the final product. And you can see DSC can tell us things like crystallinity, for example, decomposition behavior, and so on. Okay, now we'll introduce the basic method of DSC. And by definition, I think it's important to note here, this is an internationally standardized methodology. So you've got ISO standards and also ASTM standard procedures that are developed around the DSC, or differential scanning calorimetry method. By definition, DSC is an analytical method that gives characteristic thermal transitions of a material or substance. So basically, we're going to look at how the material behaves on heating and cooling. Materials where this could be useful include, for example, metals, ceramics, inorganics, and organic materials, but also, and probably most predominantly, polymers. Areas of application in the polymer sector could be things like material development, quality control, failure analysis, process development, and more. So let's look at the basic operating principle of a heat flux or heat flow DSC. This heat flux or heat flow DSC principle was developed actually going back to 1955, probably before most of us were born, introduced by a gentleman named Dr. Boersma. And in the heat flux or heat flow principle, we're looking at the measurement of an energy difference between a sample and a reference material following a controlled temperature program. So it's important to note that this can be both heating and cooling of materials. So in the heat flux model for DSC, or heat flow model, we've got a single furnace. So hopefully you can see my cursor as I circle the typical heat flux DSC cell and sensor. And you've got a heat flux sensor then, where we put a sample on one side inside of a crucible. Some people call this a sample pan. So we'll use the term, hopefully I'll try to standardize on one. I usually like to call it a crucible, but some people call it a pan, but we'll use those interchangeably. The sample sits on one side. Inside, generally it's going to be an aluminum crucible, aluminum metal, but it can be other materials as well. Depends on the reactivity, for example, of the material. So on one side you have your sample that's essentially contained or encapsulated, and then on the other side we have a reference. And the reference material is simply just the same crucible type as what we see with the sample. And then we're measuring the temperature difference here in the heat flux sensor and the heat flow behavior between the sample and the reference. Heat flow into or out of the sample. And so generally, again, the reference pan is empty. And so we're just then really getting a good feel for what's going on with the sample itself. As it compares then to the reference material. These aluminum pans can have pierced lids if you want to get have the gases to escape so that we don't get a pressure buildup, or you can use them with the lid not pierced so that we can essentially contain or encapsulate the reaction process if it better simulates what the actual process that the material is exposed to, if it best mimics that process. And then, so for example, in polycondensation reactions, we can even use pans that are called autoclave or pressurized pans that really can hold a very tight pressure down on top of the sample to keep it from pulling the lid off if there's an overpressure situation. So this kind of gives you just a general cutaway of the system. You've got a furnace heating block down below that heats this single body cell. Again, the sample and reference are inside, and we're measuring the delta T or temperature difference between the sample and the reference. And as they sit, by definition, in a DSC, these sit on a common plate. And this plate of a defined thermal resistance allows us to measure then the heat flow between sample and reference. So here we see basically a measurement of the electrical potential of the thermocouple. And so you can see two curves here. One is green, or two lines, let's say. This is the heating up of the reference material in the furnace. So let's say in a characteristic program, we're just heating up linearly at a certain heating rate from temperature A to temperature B. So you can see the aluminum metal crucible is heating up evenly then with that temperature increase of the furnace. If we compare that then to the crucible on the opposite side that has a material in it, you can see that there's an effect going on when we get to this critical point. So energy is now going into the sample. Energy is going into the sample until it finally reaches an equilibrium state and then begins to catch up. So what we're really looking at here in this example is a melting behavior of the material. Energy goes in until the sample is fully melted, and then once it's fully melted, it begins to catch up with the reference crucible. Okay, so we're looking here on this left-hand axis at a microvolt signal, again, the electrical potential of the thermocouple, and we're looking at that then on the x-axis as a function of time. And that gives us this comparison between the two, reference and sample crucible. So now what the computer can do for us is perform some mathematics on this, and on the left-hand axis here, we're looking at the delta T. we're subtracting the temperature of the sample from the temperature of the reference and looking at that again as a function of time in the x-axis. And we can see then that we can actually then quantify an area. And that area of that curve is going to tell us about the heat of reaction. In this case, we're looking at a melting. And generally, that heat of reaction is expressed in joules per gram. It's energy per gram of sample. So if we take the melting of indium on a non-calibrated instrument, it's a non-calibrated, meaning it's not calibrated to really tell us that amount of heat flow that's under the curve. So if we just look at the raw signal, let's say, in DSC, we get this peak as we go through the melting behavior, but it's only reading out, and it's a unit maybe that we really can't use directly, which is microvolt seconds per milligram. So we're going to show you the conversion process to get that into something we can use and compare quite nicely, which is the energetics, or the joules per gram. I'm going to make a note here. You see exo, the terms exo and endo, you'll see from time to time. That's exothermal and endothermal behaviors. It really just depends on your preference. In this case, most everything that we show is going to have exo behavior going down and endothermal behaviors going up. But this is just a function of the software. It's just a simple click, and you can change the direction whichever you're most comfortable with. Has nothing to do with the mathematics. It's just which way you kind of prefer to think about energy. In this case, we see energy being put into the sample to melt it, and so I think some people like to see endotherms going up. If you prefer to think of it as heat going out, if it's an exothermal behavior, then you might like your exotherms to point upward. So it's just a point of preference. So what we're going to do here is calibrate then the sensitivity. We're going to convert that microvolt signal into something that we can use, which is milliwatts. And we do that by comparing against standard materials, standard reference materials with known melting behaviors, substances like indium, tin, zinc, or bismuth. So this conversion process then, through calibration, we can, by comparing these materials of known heat flow behaviors in the melting point, we can then get or compare then the melting of our sample behavior or the other any thermal behavior, and get then the energetics expressed in millijoules. We call that a sensitivity calibration. So now this maybe looks more familiar to you. We've got the melting of indium expressed more commonly in joules per gram. So here on this on the x-axis we have the temperature, and on the y-axis we have now, instead of that microvolt signal, we have milliwatts per milligram. And then when we integrate the area under the curve here, we're going to express that in joules per gram. Some of the things that we can derive in terms of material properties by DSC, we can get direct thermal values like the glass transition. We'll talk about that in a little bit more detail in a few minutes. That's where the material goes from a more rigid to a more pliable, a little bit more flexible state. Melting temperatures, crystallization temperature, reaction temperatures, endothermal heat of melting. We just talked about that with this example of the indium metal. Exothermal heat of crystallization, exothermal heats of reaction, and also specific heat capacity. In addition, DSC can give us information like degree of crystallinity, degree of curing, and how that those can actually relate to the mechanics or strength or toughness of a material. It can also tell us, give us some ideas based on the shape of the melting peak about distribution of molecular weight, and also crystallization behavior. We've got a good example of that coming up a little bit later in the presentation. And then another area where some of you might be working is in the context of oxidative stability, areas where you've got materials, for example, the cable insulation that has to not oxidize after exposure to certain temperatures or certain amounts of time. So you might put in different antioxidant packages to try and stabilize that polymer. And so that's a standard test called oxidative induction time, OIT, that we can use the DSC to look at the time it takes for a material to oxidize at a fixed temperature, or maybe if we look at it dynamically, we can look at actually what temperature the material starts to oxidize. So if we look at the standard temperature program by DSC, this is pretty neat if you think about it in the context of polymers. Usually we do a first heating, and then that's what we see here. And then we might hold for a minute or so, and then cool down in a controlled fashion, and then hold a little bit longer, and then our second heating. Okay, the first heating here, it reflects the entire thermomechanical history of the sample. When we compare the thermal profile, the DSC profile of a sample in the first heating, we're going to be looking at thermomechanical history. This includes the impact of the production or the manufacturing process, the storage conditions, as well as you'll see the effects of sample preparation. Now, after we get through the melting point for what we'll define as semi-crystalline thermoplastics, or the glass transition temperature for amorphous polymers, after we get through those points, this history is erased. A controlled cooling then follows. That's what we see here. The controlled cooling follows, and this way we are able to establish then the same thermal history at the beginning of the second heating for all the samples to be compared. So when we're looking at then just the effects of the polymer itself, the base polymer, that's where the second heating can be really important. We're going to show you some examples a little bit later today during the webinar of when we compare materials on the first heating, then comparison in the second heating as well. Now the second heating is going to show us, again, the material properties, and that's why it's usually going to be used for the material characterization itself. The first heating is usually looked at if we're looking at the processing differences. And if the properties of a preconditioned sample need to be determined, or we want to follow a reaction, for example, like curing. Polymers, probably everybody knows, they're long chain molecules, and they can usually kind of exist in two states. Depends on the type of polymer. We've got amorphous polymers where there's really no defined structure or shape of the polymer chains. You can kind of think about them as if you've ever boiled spaghetti noodles and they sit in the bottom of the pan. There's no real orientation. They're just kind of laying all over each other in kind of a disorganized state. So that would be kind of a good way to think about an amorphous polymer. And so what we'll see with amorphous polymers by DSC is things like the glass transition, where the material kind of relaxes. But in a semi-crystalline material, a semi-crystalline polymer, there's going to be two domains. Some of the amorphous materials, like we see up here, you'll see kind of loosely laying around. But then we also have crystalline or more ordered structures. And those structures, when we heat them up, usually we're going to be able to see then the melting behavior. So when we talk about semi-crystalline, we're going to look at things like melting behaviors, but possibly also glass transition. But then in amorphous polymers, we're going to be looking at mainly the glass transition. Okay, so let's get into some examples. Typical effects in polymers. If we look at an amorphous thermoplastic resin, again, we're going to be looking at the glass transition. So here's an example of an amorphous thermoplastic polycarbonate. Now, by definition, the glass transition is a reversible transition in amorphous materials or in amorphous regions within semi-crystalline materials. And what we're at that point, what we're seeing is we're going from a hard or relatively brittle state into a softer or more rubbery state. And I guess the change in physical properties here, specific heat capacity, glass transition is a change in specific heat capacity. Again, going from a glassy to a rubbery state. It's like a softening point. So I guess one example I could think of here on a winter day is your automobile tires. You'd really like to have your glass transition be as low as possible so that your tires are pliable and flexible in cold weather. You wouldn't want them to be hard, so that if you hit a pothole or a rock under cold conditions, that the material would shatter, right? You wouldn't want that. You want your tires to be soft and pliable, even under very cold conditions. So we want to have that glass transition where it goes from that hard or glassy state to the rubbery state. You want to make that as low as possible so that your tires are useful even in extremely cold conditions. That's just a good example. So here we're looking at polycarbonate in this example. It's 5 milligrams of material heated in an aluminum metal pan in the DSC under nitrogen at 20 degrees a minute. And so as we heat up, we see a transition here. It's a shift in heat capacity. That's our glass transition. And you can also see the reverse then in cooling. So we're going to evaluate that automatically with the computer. And you see then we get, let me try that again. We see here the midpoint of the glass transition at about 147.5 degrees C. And then there's also this change in heat capacity of about 0.2 joules per degree Kelvin. Okay, that's your shift in the heat capacity. So we're going to compare that then. We just looked at an amorphous material. Let's compare that then to the semi-crystalline thermoplastic resin. In this case, PPS, or polyphenylene sulfide. And by definition, macromolecules of semi-crystalline thermoplastic polymers, they form these crystalline structures. Remember from that graph that I showed you, or the photograph from before, you've got these ordered structures in addition to some amorphous or disordered polymer chains kind of weaving their way in between. If we increase the temperature, these crystalline structures will go through a phase transition from solid to liquid, and we call that melting. Melting is an endothermal process. In polymers, melting tends to happen over a broad region compared to metals, for example, which it's usually a very sharp melting point. Now, crystallization is the reverse of melting. It's an exothermal change from liquid to solid. So here we look at this PPS material, polyphenylene sulfide. We're heating up at 10 degrees a minute. And you can see there's a transition here. And we'll define that in a moment. And then followed by a large transition here. So now, and you can kind of guess what this is because that's the direction we're going with semi-crystalline materials. Is going to be the evaluation, for example, of the melting point. So as we heat the material, similar to what we saw in the previous example for polycarbonate, we've got a glass transition where it goes from this rigid to a more pliable state, you could say, and then we take the material then through the melting point. If we do look at the cooling curve, then we see the recrystallization where those molecules start to reorient themselves into a crystal structure. And again, the same glass transition down below, but this time where we went from the opposite state, from the softer state to the harder state. Now, kind of a third area of polymers that we haven't talked about yet is the area of thermosets. So thermosets, generally we're going to look at things like curing behavior. And the curing behavior is refers to the hardening of a polymeric material by cross-linking as the molecules link up and connect to form these more rigid, I guess I'd maybe call them bridge structures. That's cross-linking. And so we've got cross-linking or covalent bonding can form this curing process. Now, the curing process of a thermoset material can be initiated by chemical additives, by adding something to the material, by UV radiation. A good example there is probably most of you now have been to the dentist and had them put a UV light if you're getting a crown or if you're getting a ceramic filling. And generally, those are going to be cured with UV radiation. So that's hence the blue light that they put into your mouth to expose to the dental material to cure it. But it could also be heat cured or electron beam cured. Now, in rubbers, the curing process we generally refer to as vulcanization. So formation of this three-dimensional network, this cross-linked structure, it's an exothermal process, and it consists of basically two parts, gelation and vitrification. So what we see here is an epoxy powder coating. And we look at this in green, we see the first heating of the material, and then in red, the second heating. So what you're really seeing here in the first heating is we go through the glass transition of the material, again, where it's becoming more loose or more flexible. But then we actually go through the curing process itself. And so you see this exothermal behavior. Again, here in this nomenclature, exothermal is going down in the downward direction. So here's your exothermal behavior in the first heating. And you can see how we're evaluating then. We can look at the peak temperature, and then you can also integrate the energetics associated with this curing. But then if we run it again in the second heating, all we see is the glass transition. And it's commonly seen that the glass transition is going to move later. So we see a glass transition that was around 71 degrees in the uncured material. If we run it in the second heating, we're somewhere up around 105. So that's kind of a general rule that the glass transition shifts upwards. But what's also, I think, important to comment on is you'll notice there is no further curing here, right? So that means in this first heating, we effectively cured or cross-linked the entire material. So if, for example, we were looking at a composite part and we were trying to determine if we'd properly cured the material in an autoclave or an oven, that when we heat that material, if we saw any curing after we've processed it, any remaining curing would tell us that maybe we didn't fully cure the material. But in this case, what you see is a fully cured material. So post-curing is definitely something that's important to look at in the area of thermosets if you're trying to make sure a material is fully cured in the first go-round. So that's some basics on principle and then fundamentals of polymers. Now let's look at applications for quality control and failure analysis. So here's a good example. A molder is looking at some recycled material, and we'll just call those PET, excuse me, for polyethylene terephthalate, PET 1, 2, and 3. And so this particular molder wants to know this recycled resin, how they compare. Am I getting the same material? Will it behave the same as all across the board? So what we're going to do in this case, we talked about this earlier. In this case, we're going to look at the melting behavior in the second heating segment after we run a defined cooling program. But we're also going to look at the crystallization behavior in the first cooling segment. Okay, so those are two areas where, in the context of PET, we might see a very good way to characterize the materials. So here's the DSC profile. We're heating up to about 260 degrees from around room temperature, and you see here and if we just look at the glass transition, it's basically looks to be about the same, 80.3, 80.8, 80.7. So the glass transition of the material, if that's all we looked at, we would probably argue that the material is the same. But if we go up into the melting point of the material, then we know there's something that's going on. There's a pretty big difference in how this material is behaving. You can see, let's get my cursor here. You can see just the shape of the peaks is completely different, at least in the case of PET 1 versus 2 and 3. Okay. Now, that kind of maybe gives us an idea that if we know that this is the closer to the good material, maybe gives us an idea that that we've got an issue with contamination in this material. So it's also really neat to look at this material on cooling and see how it behaves as well. So we take the same PET material, and as we cool it down, you can also see a pretty big difference between the peak height to width ratio from the first sample and PET sample 2 and 3. Also, you can see the start of this. This is here we're looking at the recrystallization. You can also see that the start of the recrystallization is quite a bit different as well. And so that kind of indicates to us as well that there's definitely something that's going on that's causing this material to nucleate earlier and possibly starting this curing process, or the recrystallization process earlier. So again, there's probably some kind of contamination that's in these materials, at least from what we can see comparing 1, 2, and 3. Definitely there's something that's going on in 2 and 3. And even those two are different from each other as well, 2 and 3. Now we'll look at an example of failure analysis on a molded part. This is nylon 6,6. It's glass filled, or polyamide 6,6. And what we want to find out with this particular automotive part is does the polymer that we're using have enough crystallinity? Remember, I mentioned a little bit back, crystallinity impacts the strength. So we want to know if the polymer has a sufficient degree of crystallinity in all regions of the molded part. So we're going to do that with our handy DSC. We're going to heat at 10 degrees per minute. We're going to cool down at 10 degrees a minute. But this time, we're going to be looking at the first heating segment. If you remember, I said the first heating gives us the entire thermomechanical history of the sample. Okay? So that's what we want to see here because we're going through this forming process. And we're going to take 2 samples and look at the one from an area of this rib, and then take a piece out of this main body and compare the two. So this is pretty neat. Again, this is the first heating now, so we're looking at processing conditions, the effective thermomechanical history. And so you see we've got several different things going on. Let's get my cursor here. Here's our glass transition. And even if we just start with the glass transition, you can see a big difference between the rib piece and the body piece. I'll call it the body piece. Yeah, it's body. And it's about 42 degrees is the glass transition versus 53 or 54 degrees. And if you remember, nylon 6,6 or polyamide 6,6 is really prone to pick up water. And generally what we're going to see is if it's the more water in the material, I think that the impact on the glass transition is to bring it to a lower temperature. So it kind of indicates to us, we can really surmise that maybe there's some water uptake or moisture uptake at this point in that particular area of the part. And we've got another peak going on here. But then as we get up and we look at the melting point is I think what's most interesting. You can see that the melting point between the two looks fairly close. Temperature's pretty close, but I think what's neat here to look at is this recrystallization before we go into the melt, and that's important because that tells us really could tell us quite a bit that maybe this material is after it's been formed is being cooled too quickly. So that's allowing then some of this material in the DSC, we can see some of it recrystallizing. And that tells us then that the crystallinity in the rib area the material's not as crystalline in the rib area as it is in that body area. And that tells us that we may have some issues with strength in the area of that rib. Okay, so that's why I think if this thing had been processed or cooled down more smoothly, we probably wouldn't see this. So that's something that's pretty important. Now let's go to another example. This is an elastomer. Curing of, we already talked about thermoset materials, but this is a thermoset type elastomer. In this case, we're going to look at a fluoroelastomer, FKM, and we look at things like glass transition and curing. Remember what we saw with that epoxy resin back a few slides ago. And now we're going to see something similar in the area of this fluoroelastomer. Okay. I guess I want to mention here also a really important takeaway point is the fact that there are some materials when we want to look at processing conditions, we looked at the first heating. When we want to look at the base material, we were looking at to compare different samples based on the base material. We looked at the second heating, and then but here in the area of a curing of an elastomer or thermoset type material, we can look at both heatings. It can give us some very good information about the behavior and curing of the material. So here we see. Let's get my cursor going. This is the first heating, glass transition of the material down around minus 20 degrees C of this elastomer. So it's a low temperature elastomer. We've got some kind of melting behavior that's going on here, maybe an additive of some kind that's in there. And then we go into the curing of the elastomer, or what we would call in the area of the rubber elastomers, vulcanization. So this is our curing. And then when we compare the second heating, you can see that curing is gone. So same as what we saw earlier with the epoxy resin, but we still have this the melting of this ingredient, this additive, and then the glass transition has shifted up. Remember, we said that earlier that we tend to see a shiftward up in temperature of that glass transition. So hopefully what we've done so far is give you an idea of the method, operating principle, talked about basic applications for polymers, also quality control and failure analysis for resins, molded parts, and then the curing of the elastomer. So we're going to kind of summarize things. The DSC is useful then for material development, quality control, failure analysis, process development. It gives us information on heat capacity of the material, glass transition, melting and crystallinity, recrystallization, right? We saw that in that example towards the end. Supercooling behavior, curing enthalpies, vulcanization, thermal stability, also thermoplastics. Some of the materials we could be looking at are materials like thermoplastics, blends of polymers, thermosets, paints, coatings, elastomers, thermoplastic elastomers, waxes, plasticizers, hardeners. And in the area of instruments, we have things we could be using DSC, photo DSC. Remember, we talked a little bit about UV curing, so we have a photo DSC, temperature modulated or TMDSC, high pressure DSCs to look at reactions under high pressure conditions. We also talked a little bit about oxidative induction time, things like wire and cable. We can couple those DSC instruments to FTIR to look at gases that come off, also mass spectrometer coupling, and then finally auto samplers from multiple samples. So let's just take 1 minute just to give you a quick overview of the DSCs that we have for the area of polymers. Netz offers the most recently developed instrument is called the DSC Polyma, and its brother called the DSC Phoenix. The Polyma is a very small-bodied furnace, very unique furnace design that allows for heating and cooling up to 500 degrees per minute. And that allows us to get very high sensitivity with this very small mass, very nimble furnace. And we'll talk about some other features in a moment. The smart mode interface allows us to set up methods almost in the blink of an eye. And then we've got built-in wizards. Automatic evaluation capability is really cool. You can essentially program the unit to automatically characterize and give you all the different evaluation points of the sample, glass transition, crystallization point, melting point, so forth, and just with a click of a button. And then also we'll talk in a moment about this new identify feature that's also really fabulous and new in the world of DSC. So this the bigger brother, the Phoenix model, covers a little broader temperature range. It's got exchangeable sensors, and then it's also got the ability to do photo curing, and then has a ability for coupling to gas analyzers, and then also a large sample changer for up to 64 positions, where this unit has a sample changer up to 20 sample positions. I mentioned this auto evaluation and identify. Now, this is really, really cool in the DSCs. You can essentially, with the push of a button, get reliable and very objective results by the computer to identify transitions. So it takes a lot of the guesswork then out of the evaluation process, and that's built into the software. It's user independent now. It operates by mathematics to identify the transition points. So you see here's a DSC heating curve that nylon 6.6 glass filled, and with a push of a button, we got an automatic evaluation of a glass transition, a peak here, and then also then the melting point of the material. So that's really neat. No training, operator independent. And then also what's new in the area of DSC is identify. And there's really never been anything like this. Some of you may be familiar with using FTIR or mass spectrometers to identify unknown materials based on a spectral library. Well, now we can do that in DSC as well. So this has been, I think, really a huge innovation in the area of characterization. You can start with the built-in Netz library and then add to that with your own materials. And at that point, then you can identify unknown materials based on their likelihood that's determined to identify the material. So you can see this determines that this particular material is most likely nylon 6.6, polyamide 6.6, based on its characteristic trace. It's got a 96% likelihood that it's polyamide 6.6. And you can also use this then to set up pass or fail criteria. So I think that's really useful in the area of quality control and identification. So if your curve matches, you can set windows or limits that it should match within this range. If so, it passes. If it doesn't, it fails. Really cool. All right. Other new tools that I want to mention to support your DSC work that are available just from Netz. It doesn't matter which DSC that you're using, but this tool is available from Netz immediately. It's called the DSC Sample Cutter. It's very important in DSC that your sample have good contact with the bottom of the pan. Remember the heat flux sensor, you've got the thermocouple type set up directly underneath the bottom of the pan that we saw in the very beginning. You want to have as uniform, as even distribution of your sample on the bottom as possible. So a nice flat preparation. So this new DSC Sample Cutter allows you to essentially cleave the sample into a very nice flat face. And that flat face then will sit on the bottom of the pan. And that will immediately improve your DSC results. And you can get this directly from Netz off the website, or if you're in the USA, you can get that, just type in the name Netz on Amazon, Amazon.com, and you can order it. But again, that's only for the folks in the US. There's also a new handbook on DSC, and this is terrific. I think everywhere I go, people want this handbook. It's got everything you ever wanted to know about DSC of polymers and more. It's available both in German and in English. So if German is not your first language and you prefer English, that's the one that we offer here in the U.S. headquarters. So just simply look it up on the internet, fill out the form, and you can order then this really beautifully done handbook on DSC applications, background, history, and so forth. And then finally, probably the most maybe one of the most useful tools that you'll ever see available is an app for your smartphone. And this tells you all the thermal properties of about 80 different polymers, things like glass transition, curing, not curing, I want to say melting point, crystallinity, so on. It's just got a wealth of information built into this library that also allows you to search on properties to pick the right polymers. So if you're looking for a polymer with a glass transition of around 30 degrees C, for example, you can input that into this app and it'll identify which polymers closest fit your application. So it's for any smartphone. So go to your app store, doesn't matter which one, Droid, iPhone, Apple iPhone. Go to your app store, type in the name Netz, and you'll be ready for a free download of this Polymers app. Okay, upcoming webinars. There's a lot of technical information that comes out of Netz. I think we're quite famous for that. It's really a know-how oriented company. So we've got some upcoming webinars on TGA FTIR. You can see the dates here later in January. Batteries. There's so much work going on now to characterize batteries. So battery safety with calorimetry is at the end of the month. Coupling of TGA MS for evolved gas analysis. So that's actually in French in February, early February. And then there's part 3 about battery calorimetries for rechargeable battery cells. And then production and characterization of filled adhesives in April. Upcoming U.S. seminars. We've got a training course on our STAs. That's the simultaneous TGA DSC instruments that does both measurements at one time on one sample. That's coming up at the end of February at our headquarters in Burlington. There's an evolved gas analysis training course that's right after that on FTIR and mass spectrometry and also GCMS. And then also we've got a one-day seminars. This is just a very small cross-section of what we have coming up. I'll be actually at the first 4 of these listed here in the southeastern United States, but you can see we start to work our way through the United States. So take a look at the website. You can see all these courses and one-day seminars are available to look up on the main website, netz-thermal-analysis.com. But if you come to these some of these first 4, if you're in the area where I'm based, I'd be happy to see you and get to know you in person. So that's the end of the formal part of the presentation. We do have some time for questions. If you can't stick around, I'd like to say thank you very much for your attention. But if you can stay for some questions, I'd be happy to entertain those. So let's see. I'm going to see if I can open my chat window. Does anybody have any questions? I do have one question that came in before we started, and someone asked me if I could explain the technique of temperature modulated or TMDSC, and it's very interesting. We didn't talk too much about that, but I'll give you just a quick overview, and that's also in that handbook that I described earlier that's available from Netz. But in comparison to the classical DSC, where we're employing this linear heating rate or cooling, temperature modulated DSC or TMDSC, we use a sinusoidal temperature modulation, and with an average or underlying an average heating or cooling rate. And using this technique, this sinusoidal heating, reversing and non-reversing transitions can be separated. So that means things like glass transitions or curing peaks can be separated. Or, for example, if you've got a glass transition that's superimposed with an evaporation. So when you run this sinusoidal heating, the resulting measurement, you get a reversing and non-reversing curve together with the average curve, and the average curve corresponds to the conventional DSC curve. So in the reversing DSC curve, all the effects related to the change in specific heat capacity, like glass transition, can be identified more clearly. Now, time-dependent processes such as curing, recrystallization, evaporation, decomposition, and relaxation, those, by contrast, are captured in that non-reversing DSC curve. So it's really useful. And if you're interested in that, then that's generally is part of the DSC systems that are available from Netz. I have another question, and that is regarding calibration. It says, do I need to use metal melting point standards, or can I calibrate with a sapphire standard? And the answer is you can do both. The issue with a sapphire standard is really great for fast calibration, but the issue here is that you're not going to really be able to get the actual temperature points. So if you calibrate your DSC with metal melting points, then with the standards kits that usually comes with your DSC, then you can get the energetics associated with the melting behavior in addition to those points, temperature points as well. So you're basically doing both in that calibration. If you use a sapphire standard, it's fast and it's a great way to calibrate the heat flow, but really not the temperature point. Okay, and let's see. Another question here about DSC in comparison to DMA or dynamic mechanical analysis, and kind of where would I use when, and maybe the other. I think where I find the DMA very useful in comparison to the DSC, just for example, would be heavily filled materials. If you've got a lot of filler that's in a material and not so much resin content, then the DMA might give you that looks at the physical characteristics. We apply an oscillating frequency to the material and look to see how it behaves in response to this input frequency. The DMA, particularly if a material is more heavily filled and there's not as much resin in it, like a composite part, for example, can tell you maybe give you a better example of the glass transition compared to the DSC. So I think that's, I think they're compatible. There's I call them brother techniques, but for sure the DMA is useful if you need to look at a big part, say 25 millimeters or 50 millimeters coupon of a sample, or if it's heavily filled. Let's see, any other questions coming up? Not sure if I see any others, but if I don't hear any, then you can see here at the bottom there's an email address to contact, ngb_webinar. That's ngb_webinar at netz.com. And so please send any questions there if you have further. And also you can look me up on LinkedIn. Again, my name was Bob Fidler, F-I-D-L-E-R. F like Frank, I-D-L-E-R. And look me up, and I'd be happy to see if I can answer any questions through that as well. And it'd be great if we get connected and can become friends. So thanks so much for being here today and for sharing your time on the webinar. I hope there was some useful information here, and it's just been great. I really appreciate it, and I wish you a wonderful year, and hopefully I can get to know you in the days ahead. Thank you. Bye-bye now.